Good morning. Welcome to the first session of the Sustainability and Green Track. And a big welcome to everyone watching the replay online. I want to first thank the organizers in making my talk to be a first session, because as a first session, I know everything I say will be original. My name is Qiseng Huang. I am part of the Common Hardware Group at Cisco, where one of my responsibilities is influencing implementation of low-carbon silicon and hardware design. Sustainability is very important to Cisco, as it is to many countries, companies, and people worldwide. In the next 45 minutes, I plan to share sustainability terminologies, to share AI factory background, to share illustrative examples of potential solutions, and lastly, to close with thoughts on the work ahead of us. Engineers love numbers, and I do too. For sustainability, a key number is 1.5 degrees centigrade. And where does 1.5 degrees C come from? At the 2016 United Nations Climate Change Conference in Paris, 196 parties signed the International Treaty of Climate Change. The treaty asks participants to strive to limit the rise of global surface temperature to not exceed 1.5 degrees above pre-industrial levels. By working together to limit this rise to not exceed 1.5 degrees, we may prevent planet Earth to face the following challenges. Heat waves that actually make from rising temperatures to melt and thaw Arctic ice triggering, ocean changes resulting in rising seas and weather changes, such as droughts and floods that causes species loss. By working together, you and I have the power to prevent all of the above from happening. Let's take a look on a possible path forward based on the Paris Agreement. To achieve 1.5 degrees C, carbon emissions is a common key unit that has been agreed upon. This chart gives an example of global annual carbon emissions over 1 century. This black line shows that our carbon emission has been slowly rising prior to the Paris Agreement. After the agreement, everyone agreed to work toward a low carbon scenario by implementing effective climate policies and breakthroughs in technology that causes greenhouse gas emissions to plateau and then rapidly decrease. This decline primarily reflects a shift away from burning fossil fuels for electricity, heat, and transportation toward renewable energy sources. Now, the next is, let's look at what are the key contributors to carbon emissions. Greenhouse gas protocol clearly defines 3 scopes that can be summarized as direct operations for scope 1 and 2, product use, procurement, and product manufacturing and logistics for scope 3. First component for scope 3 are the emissions from the energy that our products consume during customer use. This is the part where the goods that we sell and what the customers actually use from our products. Second component of scope 3 are the emissions of manufacturing and warehousing of components, products, and services producing upstream. Third component of scope 3 are emissions produced by transportation and distribution of our products in the value chain. These are the 3 key components of scope 3. Lastly, emissions from the operations of facilities, electricity, fuel for heating and cooling are accounted for in Scope 1 and 2. At Cisco, we are addressing climate change, setting a goal to reach net zero across our value chain by 2040, aiming to minimize operational Scope 1 and 2 emission and value chain Scope 3 emissions, the latter being our greatest hurdle as it represents over 99% of our total emissions, largely from post-sale energy use. And you can see 70% comes from the leftmost one. Our focus on reducing device power can help reduce our Scope 3 emissions, which in turn assists our customers in lowering their energy expenses and Scope 2 emissions. This approach has a broad impact, particularly given that data centers consume significant amount of global energy. In this talk, we will explore different ways to reduce our Scope 3 in the product use. Per Gartner, sustainable technology is a top 10 strategic trend. Sustainability has moved beyond risk and compliance and has become a catalyst for driving business outcomes, innovation, and creating a competitive edge. Cisco continues to embed sustainability as a foundation for innovation and AI-ready infrastructure to help our customers with their digital transformation journeys. In addition to the needs of the planet, more than ever, there is a business case for sustainability. Purpose and profit, it is not either or. It is both. Businesses today are facing a once-in-a-generation opportunity to make a transition that is both digital and sustainable. Why? Customers, employees, investors, and other critical partners are expecting us to act responsibly toward the planet, and they're scrutinizing our words and actions closely. Governments are also enacting regulations and requirements around sustainability goals, setting, and reporting. As you can see from some of the data points on this slide, operating sustainably and equitably is not just an option anymore. It is a business imperative. You can see here that according to the Accenture study, 73% of the chief executives believe that becoming a truly sustainable and responsible business is a top priority. And according to IDC report, 62% of companies believe investments in IT are extremely important to reach sustainability goals. Which is why we are having a conversation here today with you. There's a big opportunity to support innovation around sustainability. For example, countries around the world have authorized trillions of public funding dollars to accelerate digital transformation across multiple segments of industries to stabilize global recovery and promote sustainable communities. Research from Cisco's grant office are showing us 80% of the global funding falls into 4 categories of community development, digital transformation, emerging technology, and sustainability. This highlights how we are transforming data center infrastructure across 3 key phases. Our first phase is build. More and more, we are focusing on designing solutions to use less energy and resources. This decreases energy consumption. Second is deploy. With modern architectures, we enable consolidation of optimized both power and cooling, ensuring the infrastructure is ready for future demands. This increases energy efficiency. Last and third is operating. Through real-time visibility into energy consumption, and workloads in the Cisco dashboards, we're able to give our customers the tools to continually optimize resources and performance. We can transform the data center infrastructure by optimizing efficiency, visibility, performance, and cost across networking and compute infrastructure. According to International Energy Agency, data centers, including crypto and artificial intelligence, made up around 2% of global electricity demand in 2022, consuming 460 terawatt hours per year. As you can see here, storage ranks number 3 at 11%, behind 43% of cooling and 43% of servers. And storage is double digit and is going to continue to grow as we continue in the AI world. IT electricity demand shows no signs of slowing down and is estimated to grow to 3,000 terawatt hours per year by 2030. The way we build, deploy, and operate our data centers must change. Server, network, and storage consume over 50% of energy in the data center infrastructure. Cisco is leaning in with innovation to build AI-ready infrastructure, including servers, network, storage, and to provide more efficient cooling systems, improve airflow management, and precision cooling. Now, let's talk about a big change that started 3 years back. A very important metric that defines if your company has joined the big leagues is when you have achieved 100 million monthly active users. Let's compare key companies of the past 2 decades, including Instagram, Spotify, Uber, and others. As we witnessed 3 years ago, ChatGPT achieved this significant milestone in 2 short months. And that is 35 times faster than Uber. Incredibly how the fast pace of AI has actually changed the world. ChatGPT's rapid growth launched a race to build AI factories. Let's visit this chart with the new AI variable. Rather than a low carbon scenario to reach net zero, as we saw before, we're now faced with the potential of a high carbon scenario that may look like this. As the chart shows, this new AI gold can reset our path to 1.5 degree centigrade by returning us to a high carbon scenario prior to the Paris Agreement. But this does not have to be. We must accelerate our learnings of the past decade and apply this new AI use case. Apply our learnings to this new AI use case. But before we do so, let's understand the AI trend. Let's study where we are today and how we got here and where we're heading. Over $500 billion of combined CapEx investment has been made in the past 3 years by big tech. And where are we after all the spend? Let's use the 5 phases of Gartner's hype cycle to look at expectations for this review. If we look at the 5 phases, we're actually at the first 2 phases, the innovation trigger and the peak of inflated expectations. AI training, yes, OpenAI, Google, Meta, and many others have been busy releasing trillion parameter models. By the last count, Hugging Face has over 630,000 transformer models. So AI training development is in consolidation phase to pave way for AI inference. We are entering a new race for AI inference dominance. OpenAI, Google, Meta are expanding the next big build out for AI inference. At the same time, so are enterprises retrofitting existing IT infrastructures to meet this AI challenge. Let's take a look together at the generative AI infrastructure spectrum. Tens and thousands of GPU clusters have been built in the past 3 years to run and train large language models. Enterprises are now reaping the benefits from the massive investments for AI inference in 2 ways. Optimization by fine-tuning pre-trained models. This workload infrastructure is significantly less, smaller AI compute required. But as you can see also from the usage, right, the training is moderate and inference is moderate. Additionally, using the results of the optimized model with retrieval augmented generation, even with smaller set of AI compute can be done. So as we can see, we're transitioning into 3 different models, 3 different usages, and 3 different AI factories. The resulting AI infrastructure needed for enterprise is significantly different from that of the web scalers. But there are also tens and thousands of enterprises running independently that is not so optimal for carbon reduction. So the next sections, we are going to deep dive and look at how we can help these enterprises refactor for the AI infrastructure in a very responsible, sustainable, and low carbon way. And the key approach as we build new AI modern infrastructures is we ask everybody to think about in deployment. In deployment is a concept to improve utilization and increase efficiency during product life cycle to reduce carbon emission. We must continue to improve and reduce carbon emission throughout the life of a product and implement and actually deploy products that are able to do so. The first is something we know well, which is 80+. 80+ is an enabler that has driven industry to a higher power supply efficiency. And let's start with a simple example for those who actually are not familiar with 80+. A standard 80+ power supply, and let's say if the power supply is actually in need of 100 watts. With the 80+, what you get is the following. You get 80 watts of actual power and 20 watts loss. Loss is the power taken from the power grid, but that's not used by the equipment. This inefficiency is actually really detrimental to our environment because it's actually not used. And why is this important? Because over the past 3 decades, rack power requirement has increased 10 times. 10 times in the 3 decades. And by 2030, it's expected to increase by 66 times. So you can see the next 5 years, the rapid ask and the rapid rack power surge is incredible. The 20% absolute number of power loss for 200 kilowatts is significantly larger than 3 kilowatts. And you can see a 40 kilowatt loss is equivalent to having 4,000 light bulbs light up at the same time. So as you can see, that is the absolute power loss, right? It wasn't important in the past, but now as we actually scale up into 2,000 kilowatts, it becomes really, really noticeable. Let's continue to look at technologies that we can employ to help increase efficiency. A standard power supply has several stages of power conversion from the wall power to the supplying power of the device. As we saw, a standard 80+ power supply has a loss of 20%. An 800 watt output requires a 1,000 watt input from the power grid. Power supply vendors have innovated with power factor correction logic that adjusts the phase angle between voltage and current in an AC circuit such that power factor is close to unity of 1. This innovation can significantly improve energy efficiency. As you can see here, with the source power with power factor correction, the source power needed only needs to be 830 watts with power factor correction, compared to 1,000 watt before. A significant saving is 170 watts. This 170 watts translates to 17 less light bulbs. We need to continue to innovate, to actually have these technologies to push forward. Adopting the highest efficient power supply is critical to reducing energy consumption. As we saw previously, we saw the standard 80+, which is 20% loss, 80% use. 80+ was a certified standard that started in 2004. In the past decade, many innovations, including power factor correction, has enabled progressive improvement of 80+ to be at 96.5% Ruby today. This path to Ruby has not been easy. As you can see, with incremental optimization by each generation, it's only 3%, 2%, 2%, 2%, very, very slowly. And even more so, the titanium power supply 80+ was actually achieved in 2012. It's taken us almost 13 years to actually have Ruby today. This is very significant and very challenging, but we must push forward. We have an opportunity to do more. Today, 80+ achieves maximum efficiency of 50% workload of all power supplies. But 50% may not be the use case for all scenarios. For example, web scalers typically are fully utilized. Web scalers may want to have their maximum efficiency at 75% workload. Another example, enterprises are typically lightly utilized. Enterprises may want to have maximum efficiency at 25% workload. We need to do more to advance programmable, tunable 80+ power supplies to allow users to adjust and program 80+ power supplies to tune for the desired workload. This adjustment can be static or even dynamic. Optimizing at 50% workload may no longer be the best choice. And this is part of the in-deployment modernization we talk about. We should be able to adjust according to the use case, because energy is wasted without tuning for the best use case that the customer needs and the user case. Today, fans can take up to 30% of system power, and that is air cooling. Let's study how this works pictorially. The x-axis is the fan speed from 0 to 10%, and the y-axis is the fan speed from 0 to 100%. We know that fan power is cubically proportional to fan speed that is charted as follows. Now, if we pick a point that reduces the fan speed by half, we can see the power consumed drops to 1/8. Small reductions in fan speed will result in significant energy savings. Increasing fan speed slightly can sharply increase power consumption. This principle is why optimizing fan speed is a powerful lever for improving data center energy efficiency. Dynamically adjusting fans is critical to reducing energy consumption. Today, data centers adjust fan speed based on signals from heat sensors using a standard proportional integral derivative controller circuit. The limitation to this approach is heat sensors only react after temperatures have already risen, making heat a trailing indicator. By the time system detects a temperature spike, excess heat has already built up, requiring fans to work harder to bring temperatures back down. This heat buildup happens because the underlying devices are drawing more power. But traditional controls only respond after the fact. We see a chart of the power over time. And you can see, even at times of low activity, there can still be substantial power consumed because the fan is running, even though there's low activity. And this is because heat sensors are slow to respond, and the adjustment is very slow. In deployment, again, another modernization technique is called Precursor Proportional Integral Derivative Controller. Rather than waiting for the heat to build up, there's an additional knob we can use, which is monitoring power. We can monitor the power load as an early indicator of future temperature changes. The Precursor Proportional Integral Derivative Controller monitors both power and temperature, so that when the system starts to draw more power, we proactively adjust fans. This prevents excess heat from building up in the first place. Our unique approach uses a rate of change in internal energy and dynamic nonlinear gain coefficients for precise, efficient cooling. As a result, we minimize fan power use and avoid temperature spikes, keeping the system cool without unnecessary fan speed. Compared to the standard mode, Precursor mode significantly lowers power during the times of low activity. And you can see from this chart comparing the green versus the blue. The spikes that happen in the standard are no longer, you can see in the green. In deployment circularity, it's a sustainability 2.0 initiative. Programmable silicon achieved this in two different ways. The first way is a programmable silicon is our path to build once, and deploy many times. Initially, you may deploy your equipment for a large-scale web scaler with the initial set of features. Over time, with programmable silicon, you can update as you need. For example, you can add features like VXLAN, or you can reprogram it to actually do bug fixes. And even more, you can actually add more features or deprecate a feature. And more feature could be fitting in segment routing and actually deprecating VXLAN. We are achieving sustainable investment protection without need for any change in hardware through programmable silicon. A second deployment circularity with programmable silicon is that equipment ages over time. Silicon can be reprogrammed for a redeployment to different use cases that either need less scale or less performance. For example, a web scaler that actually is at end of life can possibly be repurposed to be a service provider or two service provider equipment. Or you can actually reprogram it to be a data center. And the data center perhaps originally being used in the United States and moving it to France or moving it to Asia. And lastly, if you think about enterprises actually use features actually several years after a web scaler went. An aged web scaler equipment can be reprogrammed to be enterprise and used in many different campuses and companies. Again, achieving sustainable investment protection without need for any change in hardware is a very important sustainability circularity initiative, and being able to do in deployment is the best thing. Run to completion engine is another advancement important to sustainability. Run to completion is a model where each task runs until it's finished. And finishing means that it is an elastic capability that allows it to build once and use multiple times. Let's walk through 3 examples using a run to complete engine. This is a simple instruction using this engine that takes S cycles. This is one single engine that can actually operate one instruction. The same engine can be used to run an average instruction. Using this engine will take 8 cycles for average. And lastly, the same engine can be actually programmed to use complex instructions using that will take C cycles. An engine that's built once and that can be used multiple times in a flexible way should be our recommended future. For lowest carbon, we should strive for maximum utilization. Let's look at a challenge for a traditional congested fabric that is not fully utilized. Starting one GPU, sending traffic to another GPU. You see, in this uncongested state, traffic is 100% perfect. And we can see, this hashes to one link. And this is a really traditional network. Now, in the same traditional network, if you look at adding a second GPU, now you can see as this builds out, is that we have 2 GPU sources sending to 2 different GPU destinations. And you can see the poor hash, you see that white, because of poor hashing, both are hashed to the same link. So you can have an underutilized network. And this underutilized network can actually, as poor hash results in oversubscription testing that in the idle as we see here. And what's the consequence? The consequence of this idle link? The consequence of this idle link is that it causes congestion and 50% of the traffic is received. Only 50%. So as you can see, a congested network behaves inefficiently. And this is our traditional network using ECMP, equal cost multipath. Now, we don't want networks like this, and forward-looking, especially AI network, we do not want to waste, and we do not want to have underutilized networks. So let's look at a modern network as we build an AI factory. Similarly, we have 4 GPUs here, and we have switches talking to each other. What does the modern fabric look like? Starting as we did with a traditional fabric, we have one GPU communicating with another GPU. A scheduled fabric maximizes utilization by evenly sending data across all links. As you can see, the data from one GPU actually now half of it goes to one set of link, half 50% goes to the other link. The key thing about technology advancement today is that unlike traditional networking, we are actually in the modern network, we allow reordering. We allow outer order transmission, and we actually reorder at the destination so that we actually enable utilization 100%. So that all the packets received will actually be sent out of order because the modern network allows reordering. And I want you guys to think about, what do you think would happen? Well, unlike the previous situation, we add another GPU. And let's see what happens. Now I click to add a second GPU. As you can see now, as previously, links are fully utilized because of this scheduled fabric technology. As you can see, what it does in the scheduled fabric is it looks at the utilization and transmits data across all the links, so everything is fully utilized. And this is also possible because of reordering technology at the destination. So, as you can see, a deterministic network behaves very efficiently. So similar to before, We're looking for a fully utilized network, fully utilized power supply, fully utilized capabilities. That is a goal for the AI factory, and that is really, really important in every single technology. Additionally, we're looking to do deployment. We like to be able to reprogram, reuse our hardware time and time again in the field without forklift upgrade and taking out the equipment. Now, again, part of sustainability is actually having low carbon design. And for lowest carbon design, another innovation is actually using a blade server rather than a rack. And the blade server not only using that, also using actually a converged network. A converged network that's able to handle storage networking, management networking, and traditional networking. An example for illustration is our UCSX, modular blade servers. As you can see, for illustration purposes, this setup requires 24 chassis, 100 gig cables, 48 chassis optics for a total of 72 components. So a blade server is very compact, very modern, and able to handle both storage via FCOE and either networking. For, again, a comparison just for looking at it, the traditional way of doing it is a legacy rack server. You can see the legacy rack server, it requires significant amount of cables, optics, and fiber. And total of 624 components. And this is over 8x difference. Network consolidation and modernization can save space and material. So looking forward, we should look at how to actually innovate, compartmentalize, and basically save on components and reduce the material carbon footprint. Now, as you guys, everybody knows, you cannot manage what you cannot measure. So everything we talk about, if we can't measure it, we don't know if we're making progress. So one of the key important is telemetry. Energy management must start with telemetry. Telemetry where actually we're able to gather information on the carbon, we're able to carbon intensity, we're able to gather information on the energy consumption. We're able to gather energy on the greenhouse gas emissions and energy costs and energy mix. Carbon calculation can only be done with telemetry and significant quality telemetry so that we actually know what we're doing and if we're making progress or not. Across all our equipment, whether it's a power supply, whether it's a storage device, whether it's a networking device, or even a server device. As we mentioned previously, with this visibility, what can we do with this visibility, right? You can't manage what you cannot measure. Now we have measurement. So what do we do with this measurement? We can gain insight to monitoring, to compare and remediate. Only by being able to monitor and compare, you actually can know if one device is better than another device. Only by being able to measure and monitor and remediate will you be able to actually make forward progress. And as we can see, forward progress means we take action. We take action toward OpEx savings, reporting compliances, and architectural adjustments. These are very important actions. Visibility without insight, without action, is doing nothing at all. Similarly, visibility with insight with no action is not, you are not making anything. The three of them in conjunction is very, very critical, and we must ask all our component vendors to actually provide telemetry so we can help ourselves take action. Now, Cisco has a complete portfolio of customer-validated design, the AI factory, and that anchor on the data center, edge, co-location, and public cloud. As you can see, the foundation of what we have is at the bottom of this chart. And what do we have in terms of building this AI factory at Cisco as an illustration? We have security and observability with Splunk. Splunk is one of our, has agents able to collect all the information that you need and be able to actually provide insight and take actions based on that. We also have the Nexus data center switching. The Nexus data switching is our data center, top tier AI factory switching that's capable of 51.2T and above. Additionally, we have our UCS Classic and AI GPU clusters. This is extremely important because the thing is not only do you need networking, you need compute. And the tightly integral of the two is actually very critical to a successful AI factory. And lastly, in addition to that, we also have a Nexus dashboard Intersight. These are also similar to the dashboards we saw on the previous page. They collect exactly the same sustainability metrics of greenhouse gas, carbon intensity, energy management, and others. By being fully compliant with leading AI frameworks and management tools, Cisco here, as you can see, will work with all the PyTorch and with all the NVIDIA and all the different public and open source tools and private tools. And this is a validated design that you can take out of the box and install and test out yourself. Let's return to our path forward as we get to the closure of our discussion here today. This figure that we saw previously shows two potential global carbon emissions scenarios from a wide range of possible alternatives. This business as usual high carbon emission path, which is the red line, extrapolates recent trends in economic output and energy efficiency due to AI factory. By contrast, the low carbon scenario, the green line, was effective with climate policies and breakthroughs in technology that causes greenhouse gas emissions to plateau and rapidly decrease. We talked about many examples of in-deployment capabilities, modern network technologies that we should put in our AI factory so that we can actually reverse this red line. And we need to do that starting today. Because the later that we take action, the harder it is to close the gap. As you can see with the illustration, the gap gets wider and wider, harder and harder to close. So we need to start today. At Cisco, we're addressing climate change. We're setting goals to reach net zero across our value chain by 2040. AI does not have to be a stumbling block to our goal. Let's use our learnings of the past decade and apply to the AI factory and enable AI to accelerate our path together. Thank you for joining me today, and hopefully this is informative and you can take it back to your company and your daily lives and work to help us evangelize how to become sustainable through an AI factory. Thank you. Any questions? Sure. Right, so we do, yes, so reading questions, sorry about that, thank you, SW. So the question from our audience is that with power efficiency, should we say getting at peak, but the challenge is that actually in all systems, right, we do N+1, multiple power supply. So we actually never achieve the maximum load in terms of the requirements. So two techniques. One is one we talked about earlier in terms of tuning the power supply. we're in discussion with power supply vendors to actually be able to programmably adjust the optimal, right, away from 50%. So if you're doing dual power supplies and they're both operating at 30%, we want to be able to shift the maximum operating efficiency to at 30%. So that's a tunable capability that's under discussion. The second part is called, we have a technology called code redundancy, where actually we will look at shifting all the power to one power supply. Okay, and then as you cross over a threshold, then we actually add as we go. So it's a combination of two technologies that we actually have looked at, and we welcome to discuss with you, is that actually the power supply vendors are very eager to actually adopt that, and we're working with them right now. Yes, please.
For those power supplies, what is the ECOS 80 rating on those? Are those gold or platinum?
So currently, yes, apologies, I forgot to repeat the question. What are the ratings for 80 plus power supplies? So for now, primarily the EU standard is requirement is titanium. So titanium, I think, is 94%. That is the efficiency right now for the platinum 80 plus, and that is the EU standard. There is actually one in between, I think, 80 titanium plus, that actually are proprietary for some companies. And the shift, obviously, right now is going to higher voltages, right, with the Ruby.
Is that for single server power supplies or redundant?
So all power supplies, okay, so is that for single or redundant power supplies, right?
Yeah, because I've seen in redundant power supplies, it's meant to be that you have the capacity to switch the whole load on the one, so you never get to like titanium.
Right.
Stuff by itself.
Right. So similar to the question previously is yes. So let's say you have two power supplies, right, and each are 1,000 watts, and then the software actually uses 500 watts each. So basically, then if it's optimized at 50%, that's a sweet spot. But let's say if it actually gets 600 watts and it's spread across 300 watts each, right? If it spreads across 300 watts each, then you're right, we're not efficient. So that's why there are two technologies. One is basically we shift everything to one power supply, but then the risk, obviously, as you stated, is that you don't have a failover. So in that case with two, we're discussing with the power supply vendors to actually be able to tune the optimal power supply to be at 30%. So right now they're at 50%, but they actually can shift that curve over at Programmable, which they don't do today, and we're asking them to be able to do that. By being able to do that, they will help everybody to be programmable, and you can shift the optimal point. But that's not available today, and that's under discussion.
Stay for mine, you'll see where I'm coming from.
Okay, I will be here.
Regulatory side, on the next one.
Okay, great. Yes, okay. So thank you very much, everybody. I appreciate for you being here, and goodbye.